In the last several modules, we learned about space management within your memory. In today's module, you will learn about different space management file systems. There are many different file systems used by popular operating systems. Just to name a few, for instance, DOS and Windows use file systems that is known as FAT, File Allocation Table, and there are several variants, FAT12, FAT16, FAT32, depending on the number of bits used in the file allocation table. And Linux has several variants of ext, ext2, ext3, ext4, and then Mac OS X uses HFS, Hierarchical File System. There are many other file systems that are becoming popular like ZFS or Butter file system, which is based on B3, BTRFS. But the question is, why do we need to use these file systems? So let's say you have an image file of American Robin shown in this page. The image may be in a different format like a JPEG, PNG, bitmap. And then the image may be stored in a different operating systems, use different file systems. Maybe you're using Windows, Linux, or OS X. But at the end, the image contents have to be stored as block of bytes into your physical drive. One of the main jobs of the operating system is to provide an easy-to-use interface for the user to work with files or directories. When working with files, users usually view a file as a contiguous sequence of bytes read from one storage device somewhere. In reality, the file contents may be divided into smaller blocks which are not stored contiguously. They may be stored non-contiguously in the storage device. And these smaller blocks may also be read from several storage devices, not just from one. This is pretty much similar concept that we learn in memory management. Contiguous logical address space are mapped into non-contiguous physical frames in your RAM. There's also a major difference between the user point of view of files versus the system point of view of storage devices. For instance, user thinks in terms of records, database tables, file format, whether the file is binary or text. But the operating system works in terms of block of data, disk track number, disk sector number, error checking algorithms, and so on. In addition, the system also provides the same interface to the user regardless of whether the files come from a DVD, an IDE drive, a USB drive, or a CD-ROM. And the main job of the operating system is to bridge the gap between the high-level concepts to low-level operations to the underlying storage device. And also it's becoming more common for us to use remote devices or cloud storage like OneDrive, iCloud, Dropbox, and Google Drive. Many techniques that we discussed in memory management can be carried over to file management. There's a few minor differences. In memory management, we deal with transient data in memory, and the OS does not intercept memory fetches issued by your process. But in file management, we deal with persistent data that we store on a disk. And also, all accesses to the storage device must be issued through system calls. So let's look at basic system calls typically provided by operating system. There should be system calls for a user process to manipulate files and directories, to create, read, delete, and other basic operations. The OS should also provide mechanisms for the user to control access to their files. Quite frequently, we use files to store important data like your text files, wedding pictures, and so on. And we expect file systems to provide reliable storage services. In case of unexpected interruption like loss of power, Your files may not be properly stored to the storage device, and a reliable file system should allow the user to recover their data. When you write a C program that uses system calls like open, read, write, and close, you may not realize the amount of work performed by the operating system on your behalf. After learning from this module, I hope you will appreciate the amount of work, the amount of low-level details carried out by the operating system to complete all these system calls. When discussing memory management, we learned that operating systems depends on a number of internal data structures like page tables, segment tables to perform its work. Similar data structures will be used by the operating system to do file management. There will be data structures created one per process and also system-wide data structure to keep the state of the entire system. Another important difference in file management, some of these data structures must be persisted on the storage device, and they are also read at boot time for the system to initialize its data structures. Let's look at the many different options a program can access data from a file. The commonly used access methods are sequential access, random or direct access, and a combination of index sequential access method. And the cost of sequential access is on average ON, which is linear, and the cost of direct random access is O1, and the cost of index sequential access method is on average log n. Before talking about the three access methods, let's first understand the difference between the two record formats, variable size or fixed size records. A file can hold records of uniform size or variable size. For instance, in a typical database table, each record is a fixed size. For illustration here, we will use C code for our example. The code on the left shows how each line of the C program has different lengths, 20 characters on the first line, 2 characters on the second line, and so on and so forth. This file will be a representation of variable length record. And the code on the right is an unrealistic example of storing a C program where each line has the same number of characters, 25. This file will be a representation of fixed length records. Recall that actually the C code is internally stored as a linear sequence of bytes, like what you see here, and the red characters are new line characters that separate one line from the next. The benefit of fixed length records is that it is easy to jump to any line. By adding 25 or multiple of 25, we can just update the current cursor position to any line in our record. But for the file on the left, it is not easy to jump to any line. For instance, to jump 3 lines below the cursor, we do need to know the total length of the next 3 lines, and then we can add the cursor position with those numbers. The first access method, sequential, is the slowest among the three. Data must be processed sequentially. It is not possible to skip over to byte 10,000, for instance, without reading the first 10,000 bytes of the file. Typical operations for sequential access methods are read next and write next, which are operations to read or write data at the current file pointer position. The other operation is to move file pointer to a desired position without reading or writing any data. And this function is usually called skip. But skip operates at the cost of ON. The second access method, random or direct access, is much faster than sequential access method. But for this method to work, each record in the file must be of fixed length or uniform length. In addition to the read next and write next operations, random access method provides a function to position the file pointer to a specific record. The position file function takes a record number to position the file pointer to a specific record, and this function operates in O1 or constant time. The next access method we will discuss is index sequential. But to understand the motivation behind the access method, let's use an analogy of searching for a particular word in a thick book. So let's say we have a book of 500 pages and each page has 100 words. So we have a total of 50,000 words in a book. So what is the cost of searching for a particular word? With 500 pages total and 100 words per page, we have a total of 50,000 words to search sequentially. If we scan from the beginning of the book until the end, on average, we have to do 25,000 comparisons. Because if the word is found towards the beginning of the book, we have to make only one comparison. But the worst case, when the word is found towards the end of the book, we have to make a total of 50,000 comparisons. That means on average, we have to do 25,000 comparisons. But what if the book has several index pages that show a list of words in alphabetical order and the page numbers where the word can be found? Something like you see here. Let's further assume that we have 10 index pages and each index page contains 40 words. So that means we have a total of 400 index words. Now to search for a word, instead of scanning sequentially from the beginning until the end of the book, we will start scanning sequentially within the index pages. Because we have a total of 400 index words, that will cost us on average 200 comparisons within the index pages. After we find the word and the page number, we can jump to the target page, and inside the target page we have to do only 50 comparisons because each page contains at most 100 words. So combining the two effort to search for a word, in total we have to do only 250 comparisons across only 11 pages. So 10 pages inside the index page and then 1 page inside the book itself. Adding an index to the contents of a file will speed up file search. The index will allow the operating system to jump into the vicinity of the desired record, avoiding sequential search throughout the entire file. Of course, there will be a trade-off between time and space. The file size becomes a bit larger to accommodate for the index. Also, the index must be rebuilt when the file contents are significantly updated. In your data structure course, you may have learned a similar approach used in B+ trees. So the following table shows the summary of the 3 access methods discussed. Common to the 3 methods are the read next and write next functions, which allow a program to read or write at the current file pointer position. The sequential access method usually works with variable length records, and its skip operation to move the file pointer operates in ON. The direct or random access method works when each record has fixed size. Its skip to function sets the file pointer to a specific record number, and it operates in O1. By combining indexing technique, we can improve search operation to files with variable length records. Its find function operates in log_n. Implementation of indexing technique borrow the same idea as page table in memory management with paging. The entries in a page table takes the MMU to the frame where one particular logical page is placed in RAM. Likewise, each entry in the index block of a file takes the file manager to the corresponding data block where a particular record is found. The example in this page assumes that we are storing user password pairs. The index block holds a pair of username and block number, and these pairs are sorted by the username. The first index entry shows where blocks of username beginning with Abram can be found, which is actually block 877120, which is this block. The second index entry shows where to find the block of username beginning with Crawford, which is in block 1641. Each data block holds user ID password pair, also sorted by user ID. Let's say you're looking for Ben's password. Because Ben is between Abram and Crawford, that means we have to search for Ben's password inside block 877120, which is this block. But if you're looking for Cynthia's password, because Cynthia is after Crawford but before Dolimar, that means you have to search for Cynthia's password in block 1641, which is this block. So using this example, let's assume that each index block can hold 30 pairs of user ID and block number, and each data block can hold 20 pairs of user ID and password. So altogether, the total capacity of our file will be 30 times 20, which is 600 user ID password pairs. But what if we do need to store more than 600 items? In that case, we have to use a multi-level indexing scheme, which is similar to multi-level paging technique in memory management. Each entry in the top level index points to the lower level index block, and each entry in the lower level index block points to the actual data block where you can find the user ID and password pair. In this illustration, the top level index block shows two entries, one for Abram and one for Walter. This entry shows a group of users starting from Abram all the way to a user before Walter. So this entry here should be the user ID before Walter. The first two entries in the lower level index block shows Abram and Crawford. This means that block 877120 holds our user ID between Abram and all the way but not including Crawford. So the last entry here should be the user ID immediately before Crawford. So with this example, because each index block can hold 30 user ID and block number pair, the two-level index block can hold up to 900 user ID and block number pairs. Given each data block can hold 20 user ID password pair, then the total capacity of our file will be 900 times 20, which is 18,000 user ID password pairs. Just a refresher on the structure of B+3 that you learned in data structure class. The root node tells us to search for values less than 42, we have to follow the left pointer. To search for values between 42 and 87, we have to follow the middle pointer. And to search for values greater than 87, we have to follow the right pointer. The second level index nodes will direct us further into the actual data block to search. So let's say we are searching for 50. The root node directs us to follow the middle pointer, and to search for 50, the next layer index block directs us to follow the left pointer, which will direct us to this data block, and 50 is found inside that block.